This article is about a part of game theory. For video gaming, see cooperative gameplay. For the similar feature in some board games, see cooperative board game in game theory. A cooperative game is a game where groups of players may enforce cooperative behavior. Hence the game is a competition between coalitions of players, rather than between individual players. An example is a coordination game, when players choose the strategies by a consensus decision-making process. Recreational games are rarely cooperative, because they usually lack mechanisms by which coalitions may enforce coordinated behavior on the members of the coalition. Such mechanisms, however, are abundant in real-life situations. Mathematical definition. A cooperative game is given by specifying a value for every coalition. Formally, the game consists of a finite set of players, called the grand coalition, and a characteristic function from the set of all possible coalitions of players to a set of payments that satisfies. The function describes how much collective payoff a set of players can gain by forming a coalition, and the game is sometimes called a value game or a profit game. The players are assumed to choose which coalitions to form, according to their estimate of the way the payment will be divided among coalition members. Conversely, a cooperative game can also be defined with a characteristic cost function satisfying. In this setting, players must accomplish some task, and the characteristic function represents the cost of a set of players accomplishing the task together. A game of this kind is known as a cost game. Although most cooperative game theory deals with profit games, all concepts can easily be translated to the cost setting. Duality. Let be a profit game. The dual game of is the cost game defined as intuitively. The dual game represents the opportunity cost for a coalition of not joining the grand coalition. A dual profit game can be defined identically for a cost game. A cooperative game and its dual are in some sense equivalent, and they share many properties. For example, the core of a game and its dual are equal. For more details on cooperative game duality, see for instance, subgames. Let be a non-empty coalition of players. The subgame on is naturally defined as, in other words, we simply restrict our attention to coalitions contained in. Subgames are useful because they allow us to apply solution concepts defined for the grand coalition on smaller coalitions. Properties for characterization. Superadditivity. Characteristic functions are often assumed to be superadditive. This means that the value of a union of disjoint coalitions is no less than the sum of the coalition's separate values. Whenever satisfy monotonicity, larger coalitions gain more. This follows from superadditivity if payoffs are normalized so singleton coalitions have value 0. Properties for simple games. A coalitional game is simple if payoffs are either 1 or 0, i.e., coalitions are either winning or losing. Equivalently, a simple game can be defined as a collection of coalitions, where the members of are called winning coalitions, and the others losing coalitions. It is sometimes assumed that a simple game is non-empty or that it does not contain an empty set. In other areas of mathematics, simple games are also called hypergraphs or Boolean functions. A simple game is monotonic if any coalition containing a winning coalition is also winning, that is, if and imply. A simple game is proper if the complement of any winning coalition is losing, that is, if implies. A simple game is strong if the complement of any losing coalition is winning, that is, if imply. If a simple game is proper and strong, then a coalition is winning if and only if its complement is losing, that is, IFF. A veto player in a simple game is a player that belongs to all winning coalitions. Supposing there is a veto player, any coalition not containing a veto player is losing. A simple game is weak if it has a veto player, that is, if the intersection of all winning coalitions is non-empty. A dictator in a simple game is a veto player such that any coalition containing this player is winning. The dictator does not belong to any losing coalition. A carrier of a simple game is a set such that for any coalition, we have IFF. When a simple game has a carrier, any player not belonging to it is ignored. A simple game is sometimes called finite if it has a finite carrier. The Nakamura number of a simple game is the minimal number of winning coalitions with empty intersection. According to Nakamura's theorem, the number measures the degree of rationality. It is an indicator of the extent to which an aggregation rule can yield well-defined choices. A few relations among the above axioms have widely been recognized, such as the following. If a simple game is weak, it is proper. A simple game is dictatorial if and only if it is strong and weak. More generally, a complete investigation of the relation among the four conventional axioms, finiteness and algorithmic computability, has been made, whose results are summarized in the table, existence of simple games, below. The restrictions that various axioms for simple games impose on their Nakamura number are also studied extensively. In particular, a computable simple game without a veto player has a Nakamura number greater than 3 only if it is proper and non-strong. Relation with non-cooperative theory. Let G be a strategic game. Then, assuming that coalitions have the ability to enforce coordinated behavior, there are several cooperative games associated with G. These games are often referred to as representations of G. The two standard representations are the alpha effective game associates with each coalition the sum of gains its members can guarantee by joining forces. By guaranteeing, it is meant that the value is the max-min, e.g., the maximal value of the minimum taken over the opposition's strategies. The beta-effective game associates with each coalition the sum of gains its members can strategically guarantee by joining forces. By strategically guaranteeing, it is meant that the value is the min-max, e.g., the minimal value of the maximum taken over the opposition's strategies. Solution concepts. The main assumption in cooperative game theory is that the grand coalition will form. The challenge is then to allocate the payoff among the players in some fair way. A solution concept is a vector that represents the allocation to each player. Researchers have proposed different solution concepts based on different notions of fairness. Some properties to look for in a solution concept include efficiency. The payoff vector exactly splits the total value. Individual rationality. No player receives less than what he could get on his own. Existence. The solution concept exists for any game. Uniqueness. The solution concept is unique for any game. Computational ease. The solution concept can be calculated efficiently. Symmetry. The solution concept allocates equal payments to symmetric players. Two players are symmetric if, that is, we can exchange one player for the other in any coalition that contains only one of the players and not change the payoff. Additivity. The allocation to a player in a sum of two games is the sum of the allocations to the player in each individual game. Mathematically, if in a games, the game simply assigns to any coalition the sum of the payoffs the coalition would get in the two individual games. An additive solution concept assigns to every player in the sum of what he would receive in an zero allocation to null players. The allocation to a null player is zero. A null player satisfies, in economic terms, a null player's marginal value to any coalition that does not contain him is zero. An efficient payoff vector is called a pre-imputation, and an individually rational pre-imputation is called an imputation. Most solution concepts are imputations. The stable set of a game was the first solution proposed for games with more than two players. Let be a game, and let be two imputations if, then dominates if some coalition satisfies an. In other words, players in prefer the payoffs from to those from, and they can threaten to leave the grand coalition if is used because the payoff they obtain on their own is at least as large as the allocation they receive under. A stable set is a set of imputations that satisfies two properties. Internal stability. No payoff vector in the stable set is dominated by another vector in the set. External stability. All payoff vectors outside the set are dominated by at least one vector in the set. Von Neumann and Morgenstern saw the stable set as the collection of acceptable behaviors in a society. None is clearly preferred to any other, but for each unacceptable behavior there is a preferred alternative. The definition is very general, allowing the concept to be used in a wide variety of game formats. Properties. A stable set may or may not exist, and if it exists it is typically not unique. Stable sets are usually difficult to find. This and other difficulties have led to the development of many other solution concepts. A positive fraction of cooperative games have unique stable sets consisting of the core. A positive fraction of cooperative games have stable sets which discriminate players. In such sets at least of the discriminated players are excluded. The core. Let be a game. The core of is the set of payoff vectors in words. The core is the set of imputations under which no coalition has a value greater than the sum of its members' payoffs. Therefore, no coalition has incentive to leave the grand coalition and receive a larger payoff. Properties. The core of a game may be empty. Games with non-empty cores are called balanced. If it is non-empty, the core does not necessarily contain a unique vector. The core is contained in any stable set, and if the core is stable it is the unique stable set for a proof. The core of a simple game. With respect to preferences for simple games, there is another notion of the core. When each player is assumed to have preferences on a set of alternatives, a profile is a list of individual preferences on. Here means that individual prefers alternative to a profile. Given a simple game in a profile, a dominance relation is defined on by if and only if there is a winning coalition satisfying for all. The core of the simple game with respect to the profile of preferences is the set of alternatives undominated by if and only if there is no such that. The Nakamura number of a simple game is the minimal number of winning coalitions with empty intersection. Nakamura's theorem states that the core is non-empty for all profiles of acyclic preferences if and only if is finite and the cardinal number of is less than the Nakamura number of. A variant by Kumaba and Mihara states that the core is non-empty for all profiles of preferences that have a maximal element if and only if the cardinal number of is less than the Nakamura number of. The strong epsilon core. Because the core may be empty, a generalization was introduced in the strong core for some number is the set of payoff vectors in economic terms. The strong core is the set of pre-imputations where no coalition can improve its payoff by leaving the grand coalition, if it must pay a penalty for leaving. Note that may be negative, in which case it represents a bonus for leaving the grand coalition. Clearly, regardless of whether the core is empty, the strong core will be non-empty for a large enough value of and empty for a small enough value of. Following this line of reasoning, the least core, introduced in, is the intersection of all non-empty strong cores. It can also be viewed as the strong core for the smallest value of that makes the set non-empty. The Shapley value. The Shapley value is the unique payoff vector that is efficient, symmetric, additive, and assigns zero payoffs to dummy players. It was introduced by Lloyd Shapley. The Shapley value of a superadditive game is individually rational, but this is not true in general. The kernel let be a game, and let be an efficient payoff vector. The maximum surplus of player I over player j with respect to x is the maximal amount player I can gain without the cooperation of player j by withdrawing from the grand coalition n under payoff vector x. Assuming that the other players in I's withdrawing coalition are satisfied with their payoffs under X. The maximum surplus is a way to measure one player's bargaining power over another. The kernel of is the set of imputations X that satisfy, and, for every pair of players I and j. Intuitively, player I has more bargaining power than player j with respect to imputation X if but player j is immune to player I's threats if because he can obtain this payoff on his own. The kernel contains all imputations where no player has this bargaining power over another. This solution concept was first introduced in the Nucleolus let be a game, and let be a payoff vector. The excessive for a coalition is the quantity, that is, the gain that players in coalition can obtain if they withdraw from the grand coalition under payoff and instead take the payoff. Now let be the vector of excesses of arranged in non-increasing order. In other words, notice that is in the core of if and only if it is a pre-imputation, and to define the Nucleolus, we consider the lexicographic ordering of vectors in. For two payoff vectors, we say is lexicographically smaller than if for some index, we have an. The Nucleolus of is the lexicographically minimal imputation, based on this ordering. This solution concept was first introduced in, although the definition of the Nucleolus seems abstract, gave a more intuitive description. Starting with the least core, record the coalitions for which the right-hand side of the inequality in the definition of cannot be further reduced without making the set empty. Continue decreasing the right-hand side for the remaining coalitions, until it cannot be reduced without making the set empty. Record the new set of coalitions for which the inequalities hold at equality. Continue decreasing the right-hand side of remaining coalitions and repeat this process as many times as necessary until all coalitions have been recorded. The resulting payoff vector is the Nucleolus. Properties. Although the definition does not explicitly state it, the Nucleolus is always unique. For a proof, if the core is non-empty, the Nucleolus is in the core. The Nucleolus is always in the kernel, and since the kernel is contained in the bargaining set, it is always in the bargaining set for details. Convex cooperative games. Introduced by Shapley in Convex cooperative games capture the intuitive property some games have of snowballing. Specifically, a game is convex if its characteristic function is supermodular. It can be shown that the supermodularity of is equivalent to, that is, the incentives for joining a coalition increase as the coalition grows, leading to the aforementioned snowball effect. For cost games, the inequalities are reversed, so that we say the cost game is convex if the characteristic function is submodular. Properties. Convex cooperative games have many nice properties. Supermodularity trivially implies superadditivity. Convex games are totally balanced. The core of a convex game is non-empty, and since any subgame of a convex game is convex, the core of any subgame is also non-empty. A convex game has a unique stable set that coincides with its core. The Shapley value of a convex game is the center of gravity of its core. An extreme point of the core can be found in polynomial time using the greedy algorithm. Let be a permutation of the players, and let be the set of players ordered through in, for any, with, then the payoff defined by as a vertex of the core of. Any vertex of the core can be constructed in this way by choosing an appropriate permutation. Similarities and differences with combinatorial optimization. Submodular and supermodular set functions are also studied in combinatorial optimization. Many of the results in have analogues in, where submodular functions were first presented as generalizations of matroids. In this context, the core of a convex cos game is called the base polyhedron, because its elements generalize base properties of matroids. However, the optimization community generally considers submodular functions to be the discrete analogues of convex functions, because the minimization of both types of functions is computationally tractable. Unfortunately, this conflicts directly with Shapley's original definition of supermodular functions as convex.